Pod.ai.
Hey everyone, and welcome. We've all felt the warmth of a fire or the chill from an ice pack, right? But have you ever really stopped and wondered what's actually happening there? What's the secret chemistry behind that feeling? Well, today, that's exactly what we're going to uncover. So let's dive right in.
So here's the big question, and it seems simple enough, but the answer is just so cool. Why does a campfire feel warm, but an ice pack feels, well, cold? To solve this little mystery, we need to get a handle on one key scientific idea.
And that idea is something called a chemical reaction. Now, in simple terms, a chemical reaction is just when some substances, we call those reactants, change and become new substances, which we call products. A really great way to think about it is like baking a cake. All your ingredients, like flour and sugar, are the reactants, and the finished cake, that's the product. But here's the really important part for us today. During this whole process, energy is always either being released or absorbed.
And that whole energy exchange is where our two main characters for today's story come in. On one side, we have exothermic reactions, and these guys release heat. And on the other side, we have endothermic reactions, which do the opposite. They absorb heat. All right, so first up, let's talk about exothermic reactions. I like to think of them as the heat givers. These are the reactions that are literally releasing energy out into the world around them, usually as heat. And that's exactly why everything nearby starts to feel warmer. The most classic example, and one we all know, is just lighting a fire. When you burn wood or even just a candle, that reaction is releasing both heat and light. It's a type of reaction called combustion, and it's the whole reason you feel that cozy warmth sitting next to a campfire. And what about fireworks? Oh yeah, they're another perfect and much more dramatic example. That amazing explosion you see is an incredibly fast and powerful exothermic reaction, releasing a huge burst of energy as heat, light, and sound all at once. So here's the key takeaway. In an exothermic reaction, the final products actually have less energy than what we started with. And why is that? Well, because all that extra energy has been released. It's been given away to the surroundings as heat. Now, let's completely flip that idea on its head and look at our second type, endothermic reactions. You can think of these as the energy absorbers. They're the total opposite. For these reactions to even happen, they have to pull in energy, absorbing heat from everything around them, which, you guessed it, makes the area feel a whole lot colder. The best everyday example is melting ice. When you toss some ice cubes into your drink, the ice needs energy to melt from a solid to a liquid. So what does it do? It starts absorbing heat from the liquid it's floating in. This process literally pulls the heat right out of your drink, making it colder. That's a classic endothermic process in action. But it's not just about making things cold. One of the most important endothermic reactions on the planet is happening all around us all the time. Photosynthesis. Plants absorb energy from sunlight, and they use that energy to turn carbon dioxide and water into their food. This one single reaction is absolutely essential for pretty much all life on Earth. So what's the result with endothermic reactions? Well, here, the products end up with more energy than the reactants had at the start. And that makes perfect sense, right? Because the reaction had to absorb all that extra energy from the outside to get the job done. Okay, so now that we've met both of our main characters, let's put them side by side for a quick comparison. This is a fantastic way to really lock in the differences between them. So let's break this down. First, energy flow. It's super simple. Exothermic reactions release energy, while endothermic ones absorb it. And that has a direct effect on temperature. Exothermic makes its surroundings warmer, and endothermic makes them cooler. And finally, the energy level really tells the whole story. In exothermic reactions, the products have less energy because it was given away. And in endothermic ones, the products have more energy because they took it in. Okay, so you might be thinking, all right, I get the science, but why does this actually matter to me? Well, it turns out these reactions are a huge part of our everyday lives. On the exothermic side, the heat givers, you have things like those little hand warmers you use in the winter, a cozy fireplace, and even cellular respiration. That's the process inside our own bodies that keeps us warm. And on the endothermic side, the heat takers, you've got things like instant cold packs for an injury, the process of cooking an egg, and even sweating, which cools our bodies down by absorbing heat from our skin. Still, if you ever get the two terms mixed up, don't even worry about it. I've got a super simple memory trick that will make sure you never get them confused again.
Here it is. For exothermic, just think of the word exit. Heat exits the reaction. And for endothermic, think of the word enter. Heat enters the reaction. See? Exo for exit, endo for enter. Simple as that.
So there you have it. From the warmth of a crackling fire to the chill of an ice pack, you now know the chemical secret that's going on behind the scenes. It's this constant dance between exothermic and endothermic reactions happening all around us. Kind of makes you wonder, what other parts of your day